Chapter 12.2, Techniques for Evaluating Limits. We're going to use the dividing out technique and rationalizing technique to evaluate limits of functions. We're also going to use technology to approximate limits of functions numerically and graphically, and we're also going to evaluate one-sided limits of functions. So let's take a look at the dividing out technique. So in the previous section, we looked at limits that can be evaluated by direct substitution. In these examples here, we're going to see that when we directly substitute the number here, -3, that what's going to happen is we're going to get 0 over 0. And this has no meaning as a real number. It is called an indeterminate form because you cannot, from the form alone, determine the limit. We could use a table, and it appears that the limit of the function as x approaches -3 is -5. Now, when you attempt to evaluate a limit of a rational function by direct substitution and encounter the indeterminate form 0 over 0, the numerator and denominator must have a common factor. So basically, when you plug in this number here into the function and you get 0 over 0, there is a common factor. So after factoring and dividing out, we're going to use direct substitution again. So example 1 and 2 will show this dividing out technique. So we're going to find the limit as x approaches -3 of x squared plus x minus 6 over x plus 3. So let's try it. If we tried plugging in -3 directly into this function, -3 squared plus -3 minus 6 over -3 plus 3, we're going to get 9 minus 3 minus 6 over 0. First of all, you know that's not okay. Then at the top, you notice you're going to get 9 minus 9, which is 0. So we get the indeterminate form 0 over 0. So as soon as you get that, you know that we can take out a common factor from the numerator and denominator. So we're just going to factor. So this is x plus 3, x minus 2, all over x plus 3. And of course, we're taking the limit as x approaches -3, so just rewriting it. Now we can divide out the common factor of x plus 3. So now we're looking at what is the limit as x approaches -3 of x minus 2. And so when you do direct substitution here, you notice that we are going to get -5. So try out the next example up here. Find the limit as x approaches 4 of x squared minus 7x plus 12 over x minus 4. So if you plugged it in, first of all, you would get 0 over 0, so you know you can factor it out. So therefore, you factor it out, and you would get the limit as x approaches 4 is x minus 3. And then when you plug in 4, you would get the limit approaches 1. Now, when two functions agree at all but a single number c, they must have identical limit behavior at x equals c. So if we go back, for example, to the first one we have, and we say that f of x equals x squared plus x minus 6 over x plus 3. So that's our f of x. And we can say g of x is x minus 2, right? That's what we got after we factored it out. You can use this g of x to find the limit of f of x. So that's why the dividing out technique works. So let's take a look at example 2. Again, doing the dividing out technique. So let's factor, well, first of all, if we plugged in 1, we would get 1 minus 1 over 1 minus 1 plus 1 minus 1, which is 0 over 0. So now we can factor. So the limit as x approaches 1, we know the numerator is x minus 1. So the denominator, let's factor by grouping. X squared, x minus 1, plus 1 times x minus 1. So this is the limit as x approaches 1 of x minus 1 over x squared plus 1 times x minus 1. And then so we're finding the limit as x approaches 1 of 1 over x squared plus 1. Then we plug in 1. We find that we will get 1 over 1 squared plus 1, or 1 over 2. So try out this next example. Find the limit of x approaches 7 of x minus 7 over x cubed minus 7x squared plus 7x minus 49. Of course, when you try to plug in 7, you will get the indeterminate form 0 over 0. So we can factor, again, factoring by grouping. And then you find that you would get the limit as x approaches 7 of 1 over x squared plus 7. And so this will work. We will not get a 0 in the denominator. It's not the indeterminate form. And we will get 1 over 56. So let's take a look at the rationalizing technique. A way to find the limits of some functions is to first rationalize the numerator of the function. This is the rationalizing technique. Recall that to rationalize a numerator of the form a plus or minus b squared of m, or b square root of m plus or minus a, we're going to multiply by the conjugate. And we're multiplying that to both the numerator and denominator. For example, the conjugate of square root of x plus 4 is square root of x minus 4. So example 3, we're going to find the limit. So the limit as x approaches 0 of square root of x plus 1 minus 1 over x. So if we plugged in 0, we would get square root of 0 plus 1 minus 1 over 0. This is 1 minus 1 over 0, or 0 over 0. So in order to approach this problem, we're going to multiply by the conjugate of the numerator. So that conjugate is square root of x plus 1, and it's plus 1 over the square root of x plus 1 plus 1. So now when we multiply this, notice the numerator is just the a minus b times a plus b pattern, which is a squared minus b squared, okay, just as a reminder. So therefore, the numerator becomes x plus 1 minus 1 over x times the square root of x plus 1 plus 1. I would leave it like that, so don't multiply that through, and you'll see why in a minute. You will see now that this is the limit as x approaches 0 of x over x times square root of x plus 1 plus 1. And notice that the x's cancel out. So now we're looking at the limit as x approaches 0 of 1 over the square root of x plus 1 plus 1. Now we can plug in 0. So when we do that, we will get 1 over the square root of 0 plus 1 plus 1 is 1 over 1 plus 1, or 1 over 2. So try this example here. Find the limit as x approaches 0 of 1 minus the square root of 1 minus x over x. So in this example, you would also get 1 over 2 as well.